Section: Introduction. In this section, we discuss diffusion models, which are increasingly popular for generating images, videos, and even discrete data like text and biological sequences. Compared to autoregressive models, diffusion models can speed up generation and enhance the control over outputs. However, discrete diffusion models have three main limitations. First, they typically produce output sequences of fixed length, which is a problem for applications like chat systems that require responses of varying lengths. Second, these models use bidirectional context during generation, preventing them from reusing previous computations efficiently. Third, their quality, measured by metrics like perplexity, is currently lower than that of autoregressive models, limiting their use. To tackle these issues, we introduce block discrete denoising diffusion language models, or BD3LMs. These models blend features of discrete diffusion and autoregressive models. Specifically, they define a probability distribution over blocks of discrete variables, where the probability of a block depends on previous blocks, as determined by a discrete denoising diffusion model. Creating effective BD3LMs presents two challenges. First, we cannot compute the training objective for a block diffusion model with a single standard forward pass of a neural network. We need to develop specialized algorithms. Second, the high variance in the gradients of the diffusion objective can hinder training, causing BD3LMs to perform worse than autoregressive models, even when the block size is 1. We identify gradient variance as a significant factor contributing to the performance gap and propose custom noise processes to reduce this variance. Block diffusion generates sequences of tokens by performing diffusion within each block while conditioning on previous blocks. By leveraging the strengths of both autoregressive and diffusion models, block diffusion supports variable length generation, improves quality, and enhances inference efficiency through techniques like KV caching. We evaluate BD3LMs on language modeling benchmarks, showing they can generate sequences of any length, even those longer than their training context. Additionally, BD3LMs achieve new state-of-the-art perplexity scores among discrete diffusion models. Our discrete approach offers better likelihood estimates and generates samples with improved perplexity using significantly fewer steps than alternative semi-autoregressive methods. In summary, our contributions include the introduction of block discrete diffusion language models that are autoregressive over token blocks, support for variable length generation and KV caching, custom training algorithms for efficient batch processing, and the identification of gradient variance as a limiting factor in diffusion model performance. Our results establish a new benchmark for perplexity in discrete diffusion and move closer to matching autoregressive models. Section Summary. In this section, we introduce block discrete denoising diffusion language models, BD3LMs, to address limitations in discrete diffusion models, enabling variable length sequence generation and improved inference efficiency. We also identify gradient variance as a performance bottleneck and propose custom noise processes to minimize it, achieving state-of-the-art perplexity in discrete diffusion. Section: Block diffusion language modeling. In this section, we explore a type of block discrete denoising diffusion language models, or BD3LMs, which blend autoregressive and diffusion models. We do this by defining a distribution over groups of tokens and applying diffusion within each group. We introduce a block diffusion objective for maximum likelihood estimation, along with efficient training and sampling methods. We find that when the block size is 1, the diffusion objective has high variance, even though it aligns with the autoregressive likelihood on average. We recognize this high training variance as a drawback of diffusion models and suggest using data-driven noise schedules to lower the variance of gradient updates during training. Next, we propose to merge the language modeling approaches by modeling groups of tokens autoregressively and applying diffusion within those groups. We organize tokens into 59 blocks, each containing 60 tokens. We label each block for simplicity, and our likelihood is structured over these blocks, with each block modeled using discrete diffusion. We define a reverse diffusion process limited to each block and derive a learning objective by applying the NELBO to each term, making the model's dependencies clear. For our model architecture, we use a single neural network to parameterize the base denoiser models. This network not only provides probabilities but also supports efficient training by allowing us to compute the loss for all blocks simultaneously. We utilize a transformer with a block causal attention mask, where tokens in one block can attend to tokens in previous blocks. During training, we cache keys and values for previously generated tokens to avoid redundant computations. In terms of training and sampling, we aim to compute the loss in a single forward pass. However, denoising requires processing noisy inputs and then clean versions, meaning each block must pass through the model at least twice. To address this, we propose a training algorithm that minimizes computational demands. Instead of looping through the model multiple times, we precompute keys and values for the entire sequence in one pass and then generate denoised predictions for all blocks in another pass. We also introduce a vectorized approach that computes the loss in one forward pass by combining clean and noisy data. We design an attention mask so that noisy tokens only attend to other noisy tokens in their block and to all clean tokens in earlier blocks. This method keeps the training of BD3LMs efficient and works well with pre-training to further cut costs. Section Summary. In this section, we explore block discrete denoising diffusion language models, BD3LMs, which blend autoregressive and diffusion modeling by processing blocks of tokens, and we address the high variance in training by proposing data-driven noise schedules. We also introduce a model architecture that utilizes a single transformer network for efficient training and sampling, allowing us to compute denoised predictions for all blocks simultaneously while maintaining memory efficiency. Section: Sampling. In this section, we sample one block at a time, relying on the blocks we have already sampled. We can use any sampling method to draw from the conditional distribution, where the context is created using cross-attention with pre-computed keys and values. By caching these keys and values, we save on computation instead of recalculating them for each new block. Our block diffusion decoding algorithm allows us to generate sequences of any length, unlike traditional diffusion models that are limited to fixed lengths. We introduce masked BD3LMs, a specific type of block diffusion model that uses a masking noise process, where tokens are gradually replaced with a special mask token. More formally, we implement a noise process for each token, where the mask token is represented in a one-hot format, and we use a decreasing function for the noise over time. We follow a linear schedule for the probability of masking a token, and we adopt a simplified objective for our model, with the full derivation available in the supplementary materials. The NELBO is tight for certain cases but becomes a less accurate approximation of the true log likelihood in others. In our case study on single token generation, we find that our block diffusion parameterization is, on average, equivalent to the autoregressive negative log likelihood when certain conditions are met. We observe a perplexity gap between our block diffusion model and the autoregressive model when both are trained on the LM1B dataset. Although the objectives are theoretically equivalent, the gap arises from higher training variance in our model, as it computes cross-entropy only for masked tokens, leading to fewer tokens being used in loss gradient estimation. To address this likelihood gap, we train a BD3LM by fully masking tokens, making the diffusion objective equivalent to the autoregressive objective. Our results show that training under the block diffusion objective achieves the same perplexity as autoregressive training, and we notice a reduction in training loss variance. We confirm that adjusting the noise schedule decreases the variance of the objective, with significant differences in variance observed after training on a large dataset. Next, we discuss the issue of gradient variance in training diffusion models. Based on our observations, we propose an estimator for gradient variance to minimize this during training. While the NELBO remains unchanged regardless of the noise schedule, our Monte Carlo estimator for loss does not share this property, leading to variance that depends on the chosen schedule. We aim to find schedules that minimize the variance of the gradient estimator for efficient training. In a masked setting, we want to mask a random number of tokens, allowing the model to learn to handle different levels of noise during sampling. However, masking too few tokens makes reconstruction easy and uninformative, while masking all tokens leads to trivial learning. These extreme masking rates result in high variance gradients, and we seek to develop a new class of schedules to effectively manage this issue. Section Summary. In this section, we describe our block diffusion sampling method, which allows for the generation of sequences of arbitrary length by conditioning on previously sampled blocks and utilizing cached keys and values for efficiency. We introduce masked BD3LMs that leverage a masking noise process to improve training stability and reduce gradient variance, ultimately aligning the performance of our diffusion model with autoregressive models by optimizing the masking schedule. Section: Clipped schedules for low variance gradients. In this section, we introduce a new type of clipped noise schedules that sample mask rates for our model. We believe that these schedules can be viewed as similar to a continuous schedule where the mask probability is nearly 0 before a certain range and close to 1 afterward. This means that the function behaves linearly within that range. We recognize that the best mask rates can vary based on block size, so we learn the schedule adaptively during training. While we aim to minimize variance by isolating a variance term using squared diffusion loss, this approach doesn't directly apply to our variance estimator since we want to reduce variance across random batches. Instead, we optimize parameters to minimize training variance directly. To make this optimization manageable, we use the variance of the estimator of the diffusion ELBO as a stand-in for the gradient estimator. We conduct a grid search at regular intervals during training to find the best parameters. Our findings show that the variance of the diffusion NELBO correlates with test perplexity, and we discover a unique distribution for each block size that minimizes both the NELBO variance and test perplexity. In our experiments, we evaluate BD3LMs on standard language modeling benchmarks, demonstrating their capability to generate sequences of arbitrary lengths without conditions. We pre-train a base BD3LM using the maximum block size for a significant number of gradient steps and then fine-tune it with varying block sizes on the 1 billion words dataset and open web text. We adaptively learn the range of masking rates during training, using a grid search after a set number of gradient updates to identify the best parameters. When evaluating likelihood on the 1 billion words dataset, BD3LMs outperform previous diffusion methods, achieving notable improvements in perplexity. We observe similar results on open web text and assess the model's ability to generalize to unseen datasets in a zero-shot setting. Our evaluations show that BD3LM achieves the best zero-shot perplexity on certain datasets, surpassing other models. A significant limitation of many existing diffusion language models is their inability to generate sequences longer than the training context. The open web text dataset helps us explore this issue, as it contains documents exceeding the training context length. We analyze the generation length of 500 variable length samples, continuing until we generate an end-of-sequence token or the sample quality drops. BD3LMs can produce sequences much longer than those of other models restricted by training context size. We also assess the sample quality of BD3LMs through both quantitative and qualitative analyses. We generate sequences of various lengths and measure their generative perplexity. In our comparisons, we find that BD3LMs achieve better generative perplexities than previous diffusion methods, using significantly fewer generation steps. Our qualitative examination of samples shows that BD3LM outputs are more coherent than those from other models, approaching the quality of the best-performing models. Section Summary. In this section, we introduce clipped noise schedules that optimize mask rates during training to minimize variance in gradient estimates, adapting to different block sizes. Our experiments demonstrate that BD3LMs outperform previous diffusion models in generating longer sequences and achieving lower perplexity across various datasets, while also maintaining high sample quality. Section: Ablations. In this section, we assess the effects of our design choices in the block diffusion recipes we proposed. Specifically, we focus on two aspects: the selection of the noise schedule and the efficiency improvements of our training algorithm compared to a basic implementation. First, regarding noise schedules, we find that using clipped noise schedules is the most effective way to reduce training variance, which is linked to test perplexity. Our results show that the optimal clipped masking rates, which we fine-tune during training, depend on the block size, reinforcing our optimization strategy. Compared to other standard noise schedules, clipped masking yields the best results in terms of training variance and test perplexity. We also explore logarithmic and square root schedules that promote heavier masking for smaller block sizes, while lighter masking is better for larger block sizes, leading us to compare with square and cosine schedules. Next, we discuss the efficiency of our training algorithm, BD3LM. We have two options for computation. We can either perform two forward passes through the network or combine these passes by merging the inputs into a single attention kernel. We discover that executing this in one forward pass is often more efficient, as it reduces memory bandwidth issues by utilizing efficient attention kernels. This vectorized method results in a 20 to 25% speed up in training compared to doing two separate passes. We also compare our approach to D3PM, noting that block diffusion builds on D3PM and enhances it in three key ways. We extend D3PM to handle variable sequence lengths. We analyze the perplexity gap between D3PM and autoregressive models, identifying gradient variance as a factor, and we improve the perplexity of D3PM models. Our findings are relevant for extensions of D3PM, including those in continuous time. In relation to MDLM, we leverage its perplexity-enhancing features. While MDLM claims that their NELBO is unaffected by the noise schedule, we demonstrate that the noise schedule significantly impacts gradient variance. We also surpass MDLM in perplexity improvements, which arise not only from block diffusion but also from optimized schedules, potentially benefiting standard MDLM and D3PM models. When comparing to Gaussian diffusion, we note that performing diffusion over continuous embeddings of discrete tokens allows for the use of algorithms designed for continuous data, but results in poorer perplexity. We also address semi-autoregressive diffusion, which introduced a block version of Gaussian diffusion. Our method extends this approach and offers tractable likelihood estimates for evaluation, faster generation since our model calls are limited to the number of generated tokens, and improved sample quality. We acknowledge some limitations of our BD3LMs. Training them is more costly than standard diffusion training, but we propose a vectorized algorithm to keep the training speed within twice that of diffusion training. In our experiments, we also pre-train with a standard diffusion loss to help close the speed gap. Additionally, BD3LMs generate blocks sequentially, which may lead to similar speed and control issues as autoregressive models, especially with smaller blocks. The optimal block size varies by task, with larger sizes providing more control. Lastly, BD3LMs face common challenges of generative models, such as hallucinations, copyright issues, controllability, and the risk of harmful outputs.